Yes. So, do you remember the formula for sensitivity? What is sensitivity? Sensitivity of overall transfer function with respect to forward path transfer function is equal to how much? How much is it? And also tell me sensitivity of overall transfer function with respect to feedback path transfer function. Very good, Chetkar. 1 by 1 plus 1 divided by 1 plus GH, right? But as sensitivity of overall transfer function with respect to forward path transfer function is 1 upon 1 plus GH, right? Sensitivity of overall transfer function with respect to feed forward transfer function is feedback path transfer function is minus GH divided by 1 plus GH, right? It is how much? Minus GH divided by 1 plus GH. So what is the general formula for sensitivity? Let us say sensitivity of overall transfer function with respect to H. What is the general formula? That is dou M by dou H multiplied by H divided by M. If you want in percentage, you just multiply this by 100. Is it fine? So if at all you forget these two, then there is no problem at all. You can calculate these with the aid of this one, right? You should not forget this. If at all you forget this, you can calculate using it, right? But you should never forget this one. Is it fine? Yes. So let us say we have any system. The transfer function of that particular system is g of s, let us say, and the input we are providing to the system is r of t, right? To this particular system we are providing a time domain input of r of t. We need to get c of t. How will we get c of t? How to find out the value of c of t? Tell me. How to get the value of c of t? By taking Laplace inverse of c of s. Very good, right? So we'll whatever r of s we have, r of t we have, we'll convert this into its Laplace form. That is r of s. We'll find out r of s and we'll find out c of s. What is c of s? C of s is equal to r of s multiplied by g of s, right? So c of t is equal to what? C of t is equal to Laplace inverse of c of s. That is equal to Laplace inverse of r of s multiplied by g of s, right? This is the answer, right? So like this you can find out the time domain response of any particular system, right? Any particular system you can find it like that. Is it fine? Till now we have just revised the previous class, right? So let us say we have a closed loop system. So let us say we have a closed loop system which is like that, like this: g of s, h of s, and let us say this is our negative feedback system. So we generally use negative feedback systems only, right? So wherever we talk about a closed loop system without stating the type of feedback, right? If we say without stating the type of feedback, if we say the negative, it is a negative feedback system, a closed loop system, then we are speaking about a negative feedback system only, negative feedback closed loop system. Is it fine? Right? So in this negative feedback system, right, if at all there any problem occurs, right? Let us say in your control system, in your industry, if at all any problem occurs, what they will generally do is they will break this loop. Because of closed loop, what happens is your system might become a little unstable, right? So you might be having a doubt in your mind, which systems are more stable, closed loop systems or open loop systems, right? So let us say you have some open loop system, right? So in an open loop system, if at all in the response you get any disturbance, because of the disturbance, right, the response of your open loop system might go somewhere else and it will settle over there. It will just settle over there. Whereas in the case of your closed loop systems, what happens is, right, because of this you have some disturbance here, right? So because of the disturbance it went like this, right? It will again come back to its original state like this, right? Wherever you find any disturbance, it will again come back to its place like this, right? So number of fluctuations in a closed loop system stay for a more longer time as compared to an open loop system, right? Right. So this is the response of your closed loop system, and this is the response of your open loop system, right? So because of any difficulty, because of number of disturbances, right? So the number of seconds the open loop system, the response of the system is going to be disturbed is more in your closed loop system as compared to open loop system, and hence we say closed loop systems are more unstable as compared to open loop systems, right? Compared to open loop system, closed loop systems are more unstable, right? There are more chances of getting unstable systems from closed loop system, right? Therefore you can say closed loop systems are comparatively unstable. So closed loop systems are comparatively unstable, right? So because of closed loop, there is possibility that system might become unstable, right? So because in order to avoid that, what generally is done in industries is they will just break the feedback loop here. They will just remove the feedback connection. So but in closed loop systems, what happens is, see, even if a stable system is there, that might become unstable because of some criteria. Let us say this is the overall transfer function g of s upon 1 plus g of s h of s. By any chance, if gh became equal to -1, this becomes unstable, right? So comparatively unstable, that is what I'm saying. Closed loop systems are comparatively unstable. Of course, if an open loop system is unstable, you can use proper feedback and you can stabilize that, and we will see how we do that, right? So because in order to avoid that, what they generally do is they will just break this feedback loop, right? They will just break this feedback loop, right? Then B of s is the signal we are getting here if we are providing R of s, right? So they have given the ratio B of s upon R of s, B of s upon R of s, a name called open loop transfer function. What is the value of B of s upon R of s? Tell me. What is the value of B of s upon R of s in terms of these blocks? What is the value of B of s upon R of s? B of s upon R of s is GH, that is G of s H of s, right? Therefore G of s H of s is generally called as open loop transfer function. What do we call it as? Open loop transfer function. So wherever we see open loop transfer function throughout our control systems lecture, wherever we see open loop transfer function, we will use G of s H of s. What will we use? We'll use G of s H of s. Throughout our lecture, throughout our control systems course, wherever we see open loop transfer function, then we consider it as G of s H of s. Is it clear? There is no effect of feedback here, right? See, our motto is to prepare a feedback control system. Our motto is to design a feedback control system. By chance it becomes unstable anywhere, we will just break this loop. That's it. Our motto is to prepare a feedback control system only. There is no effect of feedback here, but feedback block, we let it be there in that place only, right? We won't disturb the feedback block, right? We will let the feedback block there in that place only. See, one more thing is, you will understand why we have taken this G of s, H of s as open loop later on, because later on while we study Nyquist plots, you will understand that, because G of s, H of s, the analysis of G of s, H of s, if we already do the analysis of this, we need not separately analyze the closed loop system. We can state the stability of the closed loop system from the analysis of G of s, H of s itself. And that is the reason why we generally consider G of s, H of s as open loop transfer function, so that if we just analyze this, we don't require a separate analysis of closed loop system. The output is still taken at C of s only. And what is the transfer function? C of s upon R of s now. C of s upon R of s is equal to how much? G of s. We are neglecting the effect of this H of s. That is it. Open loop means you are right. H of s is not present, right? Of course, right? So if we just break the loop here, is this H of s affecting C of s? Is this H of s affecting C of s? Tell me, right? This H, if we just break the loop here, this H of s is not affecting our C of s. We are just nullifying the effect of H of s on our system, right? So we are just removing the effect of H of s on our system. That is what we are doing by opening the loop, right? So trust me, there is an advantage of taking B of s upon R of s as open loop transfer function, right? If we analyze this system now, if we analyze this as open loop system now, then it will be very easier for us to analyze the stability of closed loop system. That is what I am saying. Is it clear? Right? We will just analyze G of s and H of s everywhere, and it will become very easy for us to analyze the stability of closed loop system using Nyquist plots. B of s is feedback signal. B of s is feedback signal only. If transfer function is R of s upon C of s, then what is B of s upon R of s? Both are open loop transfer functions. Wherever you see G of s, H of s, consider it as open loop transfer function, right? So it might seem a little contradictory to you, right? It might seem a little contradictory to you, but this is not the definition which I am giving, right? So this is the definition given by experts only, control systems experts only. In whatever literature you see, you will find G of s, H of s as open loop transfer function. Is it fine? So this seems a little contradictory to everyone, but see, trust me, this is given in, this is not given by me, this is given by expert literature only, right? So wherever you see G of s, H of s, consider it as open loop transfer function throughout our control systems lecture. Is it fine? So how will you find out the response of any particular system? You will find out the response of any system by applying inverse Laplace on what? C of s, right? You will find C of s and you will apply inverse Laplace on that particular thing, right? So take down this particular question. A function y of t satisfies the following differential equation: dy by dt plus y of t is equal to del of t, where del of t is the delta function. Assuming zero initial conditions and denoting the unit step function by u of t and y of t can be of the form, right? See, the differential equation which is governing the system is given like this, right? So dy by dt plus y is equal to del of t. Yeah, del of t is what? Del of t is nothing but input, right? So see here, just apply Laplace transformation on both sides. Just apply what? Apply Laplace transformation on both sides, right? Therefore, s into y of s plus y of s is equal to what? Is equal to 1. Therefore, y of s is equal to, y of s will be is equal to 1 divided by s plus 1, right? Therefore, what is y of t? Y of t is equal to inverse Laplace of this, e power minus t, right? So, is there anything wrong in this? Why is it not e power minus t? Is there anything wrong? What should I include? Yes, u of t should be included, because all the practical systems are causal systems, and in control systems we only talk about practical systems, right? Causal system means it should have output only after t is equal to 0, right? So whatever the response you get, you will just multiply that with u of t. Is it fine? Yes. So here one thing you need to notice is, see here, let us say we have some system g of s, right? G of s is our system, and r of s is the input to that, r of s is the input to that, and c of s is the output, right? So what happens if I feed an impulse input to the system, unit impulse input? If I feed a unit impulse input, what is r of s? Let us say r of t is equal to del of t. If I feed a unit impulse input to the system, what will be r of s? What is r of s? Yes, very good. Very good. R of s is equal to what? R of s is equal to 1, right? If r of s is equal to 1, then what is c of s? C of s is equal to r of s multiplied by g of s. That is equal to 1 multiplied by g of s. Therefore, c of s is straight away is equal to what? Is equal to g of s. C of s is equal to g of s straight away, right? So c of t is equal to what? You can say it is g of t. We don't represent impulse response by g of t. We generally represent inverse Laplace of g of s with h of t. You might have seen this in signals. We generally represent inverse Laplace of the system's transfer function with h of t, right? So h of t is what is called as impulse response of your system. Impulse response, isn't it? Obviously clear from this. See here, r of s is equal to 1. If r of s is equal to 1, what is c of s? C of s is equal to g of s. That's it. Very simple, right? Is there any doubt in that? If r of s is equal to 1, then c of s is equal to 1 into g of s. That's it, right? Therefore, c of t is equal to h of t, that is impulse response, right? So, see here, transfer function of the system is g of s, right? So, transfer function of the system is exactly is equal to what? Response of the system when impulse input is given, right? So, please take down this note. Take down this particular note. Transfer function of the system. Transfer function of the system is equal to the Laplace transform of impulse response. What do you mean by impulse response? Impulse response is the output of the system when impulse input is given, right? Impulse response is the output of the system when impulse input is given. Therefore, transfer function of the system is equal to the Laplace transform of impulse response. Is it fine? Right? So, wherever you see impulse response, right? So, if you just obtain the transfer function, if you just obtain the Laplace transform of your impulse response will be provided in time domain, right? Impulse response will be provided in time domain as h of t. So, if you obtain the Laplace transform of h of t, you will get the transfer function of the system. Is it fine? If you obtain the Laplace transform of h of t, you will get impulse response of the system. Is this concept clear to everyone? This we'll use everywhere in control systems. We'll use this everywhere in control systems. This is fine, right? So you must remember, this is a must remember point, right? So you must remember the Laplace transform of impulse response of any system is equal to its transfer function, right? Right? Laplace transform of impulse response is nothing but transfer function of the system. Is it clear? So let us solve an example here. Let us solve an example, right? The impulse response, of a system is given by h of t is equal to 2 into e power minus 6t. Find out the transfer function of the system. Find out the transfer function of the system. Laplace transform of impulse response. Laplace transform of impulse response is equal to transfer function of your system. Transfer function of the system. Is it clear? So how to solve this? You already have the Laplace transformation h of t. H of t is equal to how much? 2 e power minus 6t, right? Therefore, the transfer function of the system g of s is equal to Laplace transform of h of t. That is equal to what? Laplace transformation of 2 e power minus 6t. That is 2 by s plus 6. That's it. It is 2 by s plus 6. So, can you find out the DC gain of this particular transfer function? Can you find out the DC gain of this system? How will you find DC gain? U of t is not given there. Only impulse response is given. Where is U of t given? There is no word about U of t. Yes, we'll just put s is equal to 0 in this, right? Therefore, DC gain KDC is equal to what? Limit s approaches 0. The transfer function g of s, that is equal to limit s approaching 0, 2 by s plus 6, that is equal to 2 by 6, that is equal to 1 by 3. DC gain of the system is 1 by 3, right? So you remember how to find out the DC gain of any particular system, right? So what is the general representation of any transfer function? What is the general representation, right? Let us say in time constant form only. Standard representation of transfer function. What is it? What is the standard representation of a transfer function? See, I am saying you again and again, Nyquist plots is not difficult at all. You feel like you have to do a lot of calculations in Nyquist plot without calculating even a single thing. I will tell you how to solve Nyquist plots, how to obtain Nyquist plots, how to obtain data from Nyquist plots. Yes, standard form of transfer function. Standard form of a transfer function is equal to what? K times of, if it is pole zero form, it is s plus k times of s plus z, z1, s plus z2, s plus z3, so on, divided by s power r or q, whatever you can take, right? So s plus p1, s plus p2, s plus p3, so on, this is pole zero form, and if you want time constant form, kdc into sta plus 1, stb plus 1, so on, divided by s power q st1 plus 1, st2 plus 1, so on, right? So this is time constant form and this is pole zero form. These two are standard forms of representation of your transfer function. Did you people remember this or not? Please remember this. This is useful for further classes, right? If at all you stuck at basics, right? If you don't remember basics, it will be difficult for you to understand the later classes, right? So if at all you remember that, please solve the next problem. A linear time invariant continuous causal time invariant system has so and so, right? Poles and zeros are given. A unit step input u of t is applied to the applied at the input of the system. At steady state, the output has a constant value of 1. The impulse response of this system is. What is the meaning of the last three lines? R of t is equal to u of t, c of t is equal to 1, right? So what does it mean? Indirectly, what is he going to say? See, what is he giving from the last three lines is, this is your system, right? To this particular system, he has fed a unit step input, which means he has given a DC input. What is the magnitude of the DC input? Magnitude of the DC input is 1, right? He has given a unit step input, and at the output he got a steady state value of 1, right? At the output he got a steady state value of 1, which means it might have some transient value. We don't care about it. It might have some transient value, but the output steady state value is 1. Steady state value of the output is 1, which means if he is giving a DC input of 1, he is getting a DC output of 1, which means DC output divided by DC input. DC output divided by DC input is equal to 1, which means DC gain of the system is equal to 1. So this is the clue he is giving through the last three lines. He is not asking the transfer function, he is asking impulse response of the system. Just look at the question once again. A linear time invariant causal continuous time system has a rational transfer function with simple poles at s is equal to -2 and s is equal to -4 and one simple zero at s is equal to -1, right? A unit step input u of t is applied at the input of the system. At steady state, the output has a constant value of 1. The impulse response of the system is. Impulse response is asked, not the transfer function. So I am writing the transfer function of the system. T of s is equal to s plus 1 divided by s plus 2 into s plus 4. How many of you say this is the correct transfer function? If you say this is the correct transfer function, please type Y. If you say this is not the correct transfer function, please type no, N. Right? Reply with Y or N. Is this transfer function correct or wrong? Y or N? Reply now. Pamsi Krishna, Sakshi Verma, very good. Hubli Electronics, very good. So those whoever are saying no, right? So I knew why you are saying no, because there is some K term required here. K term is required here. So tell me the value of K, right? The value of K should be 8. K is not 1, K is 8. See, this is in pole 0 form. This is in which form? This is in pole 0 form, right? Only in time constant form, this constant is equal to DC gain, right? Yes or no? Only in time constant form, this constant is equal to DC gain, not in pole 0 form. So what is DC gain in this? DC gain in this is equal to, put S is equal to 0 in that. You will get K into 0 plus 1 divided by 0 plus 2 multiplied by 0 plus 4. That is equal to K by 8. Right? DC gain is equal to K by 8. Right? So K by 8 is equal to how much? DC gain is given to be 1. Right? K by 8 is equal to 1, which means K is equal to 8. Right? K is equal to 8. Put K is equal to 8 now, you will get the correct answer. Put K is equal to 8 in this, you will get the correct answer. They have given a DC input of magnitude 1 to the system, right? They have got a DC output of magnitude 1, which means DC gain of the system is DC output divided by DC input. How much is it? DC gain is 1, because 1 divided by 1 is how much? 1, right? If DC gain is 1, the DC gain of the transfer function should be 1. So they have given the location of poles as well as zeros. They have given the location of poles as well as zeros, right? Therefore, just you have to find out the value of K from the given clues, right? So K is equal to, just obtain the DC gain and equate it to 1, you will get the value of K. Once you get the value of K, you have to find out the impulse response of the system. Sir, are type 0 systems and pole 0 systems the same? Type 0 means no poles at origin. No poles at origin. Whereas pole 0 form means it is a type of representation of your transfer function. In this type, you are directly stating poles and zeros, and that is the reason why this form is called as pole 0 form. Is it clear? So C should be your answer. Yes or no? So what is the transfer function? Transfer function is 8 divided by S plus 1, 8 multiplied by S plus 1 upon S plus 2, S plus 4. Right? So they are asking you the impulse response. Therefore, R of S is equal to 1. Therefore, C of S is equal to R of S multiplied by the transfer function T of S. Right? Let us call it as T of S. Right? Therefore, C of S is equal to what? C of S is equal to 8 into S plus 1 divided by S plus 2 into S plus 4. Please watch it carefully, Siddiqui Mullah. All those examples will be covered in this. Right? So how to find out C of T? C of T is equal to what? Laplace inverse of C of S. That is equal to A by S plus 2 plus B by S plus 4. Right? If you solve this, you will get the value of A as 4. A will be is equal to 4 and B will be is equal to minus 12. Right? It is 4 by S plus 2 and minus 12 divided by S plus 4. Therefore, C of T is equal to 4 e power minus 2t minus 12 e power minus 4t. So this is the response. This is the impulse response they were asking. R of S is not 1 by S. R of S is 1 by S for unit step input. They were asking about impulse response, which means input is impulse here. So they were saying when unit step is applied, they got 1. That's it. Sorry, A is minus 4 and B is 12. A is minus 4 and B is 12. This is minus 4, this is plus 12. This is minus 4, this is plus 12. Right? This is the answer. See, I can understand your confusion. Just go through the question carefully. This is what is testing your English. Yes or no? See, unit step input is applied. When they have applied unit step input, they got a steady state value of 1. That is over there. Right? They were asking you impulse response only, which means they were asking you response of the system for impulse input only. Right? So is it clear to everyone, or else any problem now? Is this problem clear, or still any problem? The input minus 3 e power 2t u of t, where u of t is the unit step function, is applied to a system with transfer function s minus 2 by s plus 3. If the initial value of the output is minus 2, then the value of output at steady state is. Do you people know final value theorem and initial value theorem? See, if at all you want to find out the initial value of any signal, yes, you have in signals, right? Initial value of anything from its Laplace domain, right? So, initial value theorem, please note it down. Initial value theorem, limit t approaches 0 f of t. Initial value means limit t approaches 0 plus f of t. The initial value of that particular function, right, is given by limit s approaching infinity s multiplied by f of s. So if you have the Laplace domain value of, if you have the frequency function of any time domain function, right? So you can find out its initial value using this particular formula, right? So you have final value theorem also. Final value theorem. What does final value theorem say? Limit t approaching infinity f of t is equal to limit s approaching 0 s into f of s. Yes, very good. See here, initial value theorem is valid for proper transfer functions only, right? This is valid only for proper transfer functions, right? Proper transfer functions means degree of numerator is less than or equal to the degree of denominator, right? Only then this is valid. Otherwise this is not valid at all, right? So whereas final value theorem, where is final value theorem valid? Final value theorem is valid for stable f of s. For stable f of s must be stable, right? So which means if f of s is marginally stable, if f of s is marginally stable means f of t is oscillatory. F of t is oscillatory. Then this is not valid, right? Even if it is unstable, when it is unstable, f of t is unbounded. F of t is unbounded. Even then that is not valid, right? So this is not valid in the case of f of s being marginally stable and unstable, right? So if at all you don't know marginally stable or what is marginally stable or unstable, you will come to know in the stability chapter. Don't worry at all, right? So for now, just take it as final value theorem is valid only for stable transfer functions, whereas this initial value theorem is valid only for proper transfer functions. Is it clear? Clear, right? So once you got your response, you can apply either final value theorem, or else you may get your time response also. If you put t is equal to infinite in that, you will get the final value of this, right? So what is given, right? R of t is equal to what? It is minus 3 e power 2t, minus 3 e power 2t u of t. Then R of s, what is R of s? R of s will be is equal to minus 3 divided by s minus 2, isn't it? R of s is minus 3 divided by s minus 2, right? So what is the transfer function of the system? Transfer function of the system T of s is equal to s minus 2 divided by s plus 3, right? What is asked? The output C of final value of C of s is asked. Therefore, C of s is equal to what? C of s is equal to this multiplied by this, R of s multiplied by T of s, right? Therefore, R of s multiplied by T of s multiplied by T of s, that is minus 3 divided by s minus 2, minus 3 divided by s minus 2 multiplied by s minus 2 divided by s plus 3. Therefore, you will cancel these two, you will get minus 3 by s plus 3, right? So this is C of s. Steady state value of C of s means final value of C of s, right? So final value of C of s, you can find it like this. Put limit s approaching 0, s multiplied by C of s, that is equal to minus 3s divided by s plus 3. This is equal to how much? 0. Right? You can also get the final value from C of t also. C of t is equal to minus 3 e power minus 3t. C of t is minus 3 e power minus 3t multiplied by u of t. Right? So final value of C of t is limit t approaches infinity C of t. Limit t approaches infinity C of t is equal to, if you put infinite in this, e power minus infinite is what? Is 0. Right? So either way you can get the answer.